So we've learned about parametric curves and the parametric equations. Now let's apply some calculus to it. So the first thing we'll look at are tangent lines. In order to do that, we're going to need to come up with a derivative. Now we're still going to look at the graph and the curve, so we want a dy dx. However, in order to do this, we would have to manipulate our parametric equations to get our either y or x in terms of just t, or get the t by itself, and then substitute that into the other equation, and then it can be a mess. So we're going to do a more straightforward way. Think of these as differentials. We can have the dt's cancel out. If we have ddt as a operation, it's not going to work out that way. But let's use differentials. But we do have to have one disclaimer here that we don't want our dx dt to equal 0. So it's fairly equation, take the derivative of our x equation, divide them. However, when we do our second derivative, things get a little bit more complicated, because this is going to be the derivative with respect to x of our derivative. So if we apply this, it's going to be a d dt of dy dx divided by dx. Still have all of our pieces here. That's the d and then the dy. So we get the numerator there. We have a dx and a dx there. So we get our denominator there. And then our dt's are going to cancel. And then we have to take the derivative of that with respect to t, and then divide by that original derivative of x. So let's go ahead and try an example. So let's say that our x is equal to t squared, and our y is equal to t cubed minus 3t. All right, so the first thing we gotta do is take our individual derivatives with respect to t. So in order to find our dy dx, we get that. And now we could do some more work with splitting this up if you wanted to, and make it 3/2 t minus 3/2, well, 3/2t. And you can even factor out the 3/2 if you'd like. But now we want to find our second derivative. Therefore, we have to take the derivative of this part. And actually, I'm going to do it the original one just to try to make it a nice quotient rule. So it's bottom times derivative of the top minus the top, and that should be, oh, that's right, times derivative of the bottom all over the bottom squared. But now we take that entire thing and we divide by our derivative of the x equation. Now simplifying this, we would get a 12t squared minus 6t squared plus 6 all over 2t, and then that's going to be cubed. So combining that together, 6t squared 8t cubed. So here we can do some simplification. Factor out a 2 on the top and bottom. 3t squared plus 3 all over 4t cubed. All right. So we can use our original equation, or our first derivative, just like we would with other derivatives, to find where we have a vertical tangent and where we have a horizontal tangent. So with our initial equation, it was dy dx equals, and I'm going to do the unsimplified version. Now, if we want this to be a horizontal tangent, then the top has to be 0, as long as the bottom isn't. If we want it to be a vertical tangent, the denominator has to be 0, as long as the top isn't. So we want to avoid 0 divided by 0. So where is it horizontal? Set the top equal to 0. And then solve. This 1 equals 0. So therefore, t is going to equal plus or minus 1. However, we want to know what points are these. So whenever we plug in 1 to our x coordinate, we get 1. And when we plug in -1, we also get 1. For our y, a y when we plug in 1 is going to be 1 cubed minus 3 times 1, so -2. And a y at -1 is going to be -1 plus 3. So it's going to be horizontal at 2 points, 1, -2, and 1, 2. Now our t values. Now in order to find out where it's vertical, set the bottom equal to 0. And that's fairly easy. The t is going to equal 0 there. So x at 0 is going to be 0. Y at 0 is also 0. So 0, 0 is the only vertical spot. Next up, we can even check for concavity and see where it's concave up and concave down. So for that, we're going to use our second derivative. So we might have concavity changes where the second derivative is either 0 or undefined. So let's see where the top is 0. And then let's see where the bottom is 0. Now here it's going to be t squared plus 1 equals 0. So therefore, t is going to equal plus or minus square root of -1. Okay, so that's imaginary. Here it's wherever t is going to equal 0. So we already know that that point would be 0, 0. So if we would plug in a t value less than 0, oops, don't want it to equal 0, we'll plug in a -1, we would get 6 over -4. So -3/2. So this is a concave down situation. If we do this where t equals a +1, then we get 6 on top and +4, those 3/2. So it's concave up. So since t equals 0 was the only inflection point, then it's going to be concave down for t less than 0 and concave up for t greater than 0. And now if you would graph this, the graph looks something along these lines. Oh, this should hit exactly at the origin there. But we're able to see here's where we said our vertical tangent should be. And then we have two horizontal tangents at 1, 2 and 1, -2. And now something interesting is happening here out at 3, 0. That we're going to have two tangents. So in order for that to work, our t would have to equal square root of 3. And if you would look at your derivative, we end up with 3 squared minus 3 over 2 square root of 3. So square root of 3 squared is just 3. 3 times 3 would be 9. Minus 3 would be 6. We get 3 over square root of 3, which if you would unrationalize this, the same as square root of 3. So that would be the slope, the part that's going up. Now, if we would do this again, we're going to get the exact negative of that. And as we can see, one of them has a positive slope, the other one's having a negative slope. And our graph would be going this way. Next up, how do we find area? So area under a curve. Our equation for this is going to be the integral from some a to b of y dx, which is exactly what you think it would be because it's area under a curve. And there we do our f of x dx, but our f of x was always the height, whatever that y value was. Since our y value is no longer a function of x, we're going to use that y value, but we need to do a little bit of manipulation here so that we can use our t's because that's what we want. Now this a and b are going to be in terms of our x values. So we have to translate them into t values. We need to have dt's. So again, using our differentials, a dt there and a dt there would satisfy it. So we're going to go from some alpha to beta, and those are t values of our y of t function times the derivative of the x of t function dt. So now this is in terms of t, this is in terms of t, and then we're taking our integral with respect to t, or whatever your variable is going to be. So let's try this one. We want the area under one arch of a cycloid. And so our x is going to be some r theta minus sine of theta. Our r will just be a constant, so it's not going to matter. And then our y is going to be r 1 minus cosine of theta. By the way, notice something about these equations? That if we take our derivative of our x with respect to theta, you end up getting your y value, your y equation. So, speaking of which, let's take that derivative because we're going to need it. The r is a constant, whoops, and not dt. In this case, it's going to be d theta because that's our variable. So it's 1 minus cosine. So now, whenever we go to find our area, and let's go with our values from 0 to 2 pi, because that'll give us one arch. So it's going to be the integral 0 to 2 pi of our y value, or y equation, times the derivative of our x equation, d theta. So now these are both the same. We can pull that r squared out because it's not going to have any impact because it's we want everything in terms of our is. So now we're down to this. Let's go ahead and do some foiling. And from here, those two are going to be very easy. This one's going to be tough. So we're going to have to do some manipulation. Just like we did before with our trig integrals, let's use our power reducing formula. So that's 1 plus cosine of 2 theta all over 2. So splitting that up into two fractions, minus 2 cosine of theta plus cosine of 2 theta over 2. Taking our integral, 3/2 theta minus 2 sine of theta plus sine of 2 theta over 4. Now the nice thing is whenever we plug in 2 pi to this, sine of 2 pi is 0, sine of 4 pi is also 0. And then whenever we plug in the zeros, all of these would be 0. So things simplify very nicely. It's 3 over 2 times 2 pi. Therefore, it's going to be 3 pi r squared. And then whatever units squared that is. But remembering your equation, that's your y value dx. And then making your adjustment or d theta or whatever variable you're using. Next up, so in our normal coordinates, here's our equation. But we're going to need to use other coordinates. We have to change this into our parametric equations. So we're going to go an alpha to a beta now. We're still going to have our 1 plus, but now it's going to be a dy dt over dx dt all squared. And then we're going to need to put a dt on the bottom there and a dt out front there. All right, so this is kind of messy here. Both my writing and the equation. So let's do a modification of this. Now, if we would multiply this back through here, we can square root it and square it to pretty much give us the same thing. So that will allow our bottom part here to cancel. And it gives us a little bit friendlier version. of our dx dt squared plus dy dt squared dt. So it looks a little bit nicer. So let's try an example. We have the unit circle. So x equals cosine of t, y equals sine of t. And we'll go 0 to 2 pi. We want to find the arc length around this. So our x prime, or dx dt, we'll write that out explicitly, will be negative sine. Our dy dt is going to be cosine. So if we want the arc length from going 0 to 2 pi, it's going to be the square root of our x derivative squared plus our y derivative squared dt. Make my 0 look like a 0. So if we're squaring this, negative sine squared would just give us a sine squared plus a cosine squared dt. And now sine squared plus cosine squared is just 1. Square root of 1 is just 1. So we get t going from 0 to 2 pi, which gives us 2 pi units. Now, if you think of this, we are finding the arc length around the unit circle. So it's going to be a circle that has a radius of 1. And we are going all the way around the outside, which gives us circumference, which is 2 pi r. R equals 1. Therefore, we would get 2 pi. So it makes sense and matches up with what we would expect. Last thing we want to look at is surface area. So if we have a curve, whatever we're doing, and then we're going to rotate it to make a three-dimensional figure. And we want the surface area of that figure, what would we do? So our equation is going to kind of rely on our cylindrical shells idea of the surface area, not quite volume here, but surface area, is going to be the integral from alpha to beta of a 2 pi y times r it's not a dy, that's a dt. That's dy dt dt. Keeping in mind that this y is a function of t. So go with an example of checking the surface area of a sphere. So we're going to start with our x being our cosine, however big we want this equation to be, or the sphere to be. And then our y is going to be that. And we'll go from 0 to pi. So it's going to be a r that's then being rotated. So therefore, it's going to be a sphere with radius r. So our surface area is going to be 0 to pi, then 2 pi times our y value, which is r sine of t, square root of our derivative of our x would be a negative r sine of t plus derivative of our y, which is going to be an r cosine of t squared, and then our dt. So cleaning things up a bit, just like what we did before, to the square root, it's going to be an r squared sine squared plus an r squared cosine squared. Factor out the r squared, we get sine squared plus cosine squared, which is a 1. Square root of 1, just 1. But then we have a square root of our r squared, which will give us the absolute value of r. But since r is positive anyway, it's not going to make a difference. So this whole thing here just becomes r. So our equation becomes this. Take Then we get negative cosine going from 0 to pi. Cosine of pi is -1. There's already a negative there, so that's a positive 1. Minus plugging in a 0, we would get a 1, but it's already negative. Therefore, we get pi r squared times 2, which is 4 pi r squared. Unit squared because it's surface area. And that is the equation for surface area that we would expect. So we have a couple of equations here. Dy dx. So we have to, with respect to t. When we are doing our second derivative, it's going to be, so write this down. It's the derivative of the derivative, as you would normally expect, but because we are doing derivatives with respect to t instead of x, we have to do a compensation factor. We have area under the curve. It's our y x dt. Arc length, square root of our derivative with the x's plus our derivative with the y's. And then our last one is surface area. It's 2 pi y, and then essentially your surface area equation. It's a fairly easy process for doing each of them. They just become derivatives, and you're just taking, or excuse me, you're just taking derivatives of your individual equations and doing integrals.